Okay, I want to. I'm going to do a bunch of things here. I want to bring you up to date on my sense of the uh, science of methane globally, and then we'll come down mostly to the U.S. and then to New York, and I'm going to focus more on the fossil fuel side of things than on the other sources that Bruce was talking about, but I do want to reinforce that the waste sector, landfills, is a huge part of methane, and you'll see that in some of my figures later. But I want to start with, why do we even care about methane? You know, carbon dioxide is the main greenhouse gas driver, right? Everyone knows that. So that's true, but methane is a close second. So this is from the Intergovernmental Panel on Climate Change report just from last year. And bear with me a little bit here. On the left-hand side, there's it shows the net warming to date, that we've warmed the planet by 1.1 degrees. That's from the mid to late 1800s up until just a few years ago. The next little bar there is the total of the warming agents. That's the greenhouse gases that are driving that one, and they're driving more warming than we're seeing, and that's because humans are also putting gases into the atmosphere that cool things, particularly sulfur dioxide that has a role. So on the right, when we look at the details of what those warming agents are, carbon dioxide is that first one. Methane is a pretty close second, and then there are other greenhouse gases, but they're all distant seconds. So next slide, Dizzy. And I just want to emphasize that of all of the warming to date that we've seen, basically since the start of the Industrial Revolution to the present, methane's responsible for a third of it. This is not a trivial component of global warming, and it's one that's very, very much underappreciated. Next slide. Now, I was lucky enough to be at the COP21 negotiations in Paris back in 2015. We're at COP27 now. I'm not there, obviously, but in Paris, the nations of the world agreed that it was we needed to keep the planet well below 2 degrees Celsius of warming. And there's a clear recognition that anything above 1.5 degrees is dangerous. And again, we're at 1.1 degree right now. What is not obvious to most people out of that is that to reach that COP21 target, reducing methane emissions are critical. We simply cannot do it. We may not do it anyway, but it's physically impossible to do it with a focus just on carbon dioxide. We need to reduce methane emissions. Next slide. And that's shown in this figure. It's just from a nice paper. It's now 10 years old, but it's had some staying power. Drew Shindell and colleagues. Here we're looking at the global average temperature of the Earth from 1900 up until about 2011. That's the jagged line, and you can see the warming to date. And you can see that 1.5 threshold we want to stay below at the bottom of the yellowish bar there, and the 2 degree threshold, which is very, very dangerous. And then as of this paper from 2011, they have 4 scenarios they're showing us. And the first one is that green reference line. That's what the planetary warming would be if we've done nothing with greenhouse gas emissions over time. That's more or less where we are. And you'll see that we'll hit 1.5 degrees in about 8 years from now. And we are on target to do that in about 8 years from now. So this level of dangerous warming is not some far off scenario. That's where we're going. The next little bar down there that's labeled CO2 measures, that's what would have happened had we started aggressively reducing carbon dioxide emissions back in 2011. There's a lag of about 30 years before it makes any real difference in the climate system. We haven't done that, so that's bad news. But no matter what we had done, we'd hit that 1.5 threshold. The next 2 lines down are what happens if we were to reduce methane emissions and also soot, but primarily methanes, with or without carbon dioxide emissions. And reducing methane emissions immediately slows global warming and buys us some time. So it's the only way we're going to meet that 1.5 Paris target. Next slide. So where is methane coming from? And I'm giving you a global view here. The units are teragrams per year, 10 to the 12th grams of methane per year. And this is as of the end of the 20th century. And this is a table out of a textbook that I co-author of that we put out 8 years ago now. And what I want you to get out of a couple of things. What I really want you to get out of this is that it's out of date, because our understanding of methane science is changing so rapidly that our textbook from 8 years ago, it was the best we could do at the time, but it's wrong. And most of the government numbers you're getting, including some of the ones that Bruce showed, are wrong. They're out of date. And even the Intergovernmental Panel on Climate Change stuff is wrong and out of date. The IPCC doesn't use materials unless they've been published more than 3 years ago. They sort of, that's a set rule, and the science is changing faster than that. So, but just quickly here, there are natural sources of methane, and there are human-controlled anthropogenic sources. The anthropogenic sources, as the end of the 20th century, were larger. That's more true than for carbon dioxide. And there are a bunch of different ones: fossil fuels, animal agriculture, et cetera. Don't worry too much about the details here. What I want you to notice is that there's a number up there in the natural thing called natural geological seeps. And that's methane that we thought was being emitted from the Earth's crust naturally over time. Ancient fossil methane, as in the fossil fuel methane, but leaking naturally to the atmosphere. Next slide. And it turns out that's wrong. Next slide, please. So, okay, so why do we know it's wrong? This is a paper in 2017. It's by Vaz Petrenko, a brilliant scientist, University of Rochester here in my state of New York. He has a couple of other papers since then, but and this title will mean nothing to you, right? But go to the next slide and I'll tell you what it really means. Here's Vaz, and they go down to Antarctica in this case, and they're taking deep cores of ice, and the methane is trapped in the ice over time, going back tens of thousands of years, and they can date that, and they know how much methane precisely over time. What they're doing here is measuring the carbon-14, the radioactive carbon in the middle of methane. Now, methane is it's a single carbon atom with 4 hydrogen atoms around it, and most of that is carbon-12, a normal, stable carbon isotope, but some of it is this radioactive carbon isotope. And from measuring how much of it's there, we can determine at the time it was laid down how much of it was from biological sources versus these geological seeps. And what his work has shown is that we are totally wrong, that we thought there were these big natural seeps, but it turns out as of right up to the Industrial Revolution, we don't see that in the ice cores. We're seeing it's all natural biological methane right up until the Industrial Revolution, and then we start finally seeing the fossil signal. So all the fossil signal is from fossil fuels, which means fossil fuels are much more important than we thought 3, 4, 5 years ago. And again, the IPCC has not caught up with that. So here's a figure showing that. I've adjusted it. Those geological seeps are 0, and the fossil fuel numbers is proportionally more. And we know that because we know, again, from the amount of carbon-14 in methane in the atmosphere as a whole, that the totality of those two, and if the geological seeps are less, the fossil fuels are larger. So the fossil fuels are much more important than any of us were thinking 5 or 6 years ago. Animal agriculture is also important, but it's really fossil fuel. And that's really mostly, some of it's coal, but it's mostly the oil and gas industry. Next slide. Okay, I'm going to walk you through this slide. It's a little busy. I apologize for that. This is out of a little article. It's in press. I'm publishing it next month. Very few people have seen it, so you're some of the first. And if you look at the left hand, I'm looking at average methane emissions from natural gas development. Natural gas is mostly methane, and you simply can't develop and use it without having some of it emitted to the atmosphere unburned. That's not necessarily a leak. A leak suggests that it's just sort of going through holes or something. Some of this is a purposeful part of the operations, and we can get into that in questions if you like. I've separated into upstream and midstream. Those are the emissions that occur in gas fields and in the big pipelines and the big processing and storage centers, and then downstream, which I managed to misspell, sorry about that. And that's the methane that's occurring in city structures, the delivery gas line papers. So, going back 10 to 12 years ago, there's very little literature in this, but there are now hundreds and hundreds of papers, and we have a pretty good sense of what this is in the United States. So that first column there to the left is the mean value out of the preponderance of a large body of scientific literature, very recent literature in the US. And you can see, it's 2.5, 2.6% in the fields, et cetera. Some in cities, 2.2, total of about 4.8. Next column over is what the EPA says for 2015, and their numbers are substantially lower. So let's go to the next slide. Desi, yep, thank you. The International Energy Agency issued a report in February of this year, and they pointed out, using the two numbers I'm highlighting there, that the EPA has systematically underestimated for a long time these emissions. They say by about 1.7-fold, that's where that's coming from. And they say all other nations in the world do so too. Canada, everyone else, all European countries are similarly under by at least 1.7 or perhaps more so. If you look down, of course, the downstream emissions are underestimating even more, et cetera. And next slide, we'll look at that column to the right. What's going on here? Well, if we compare the right-hand column, that's what the EPA is saying for 2019. And you'll see that from 2015 to 2019, the US EPA says that those upstream methane emissions, what's happening in the fields, what's happening in the process plants and stuff, have gone down substantially, almost by half. And so when we compare what the peer-reviewed literature says, independent verifiable measurements, and hundreds of them, with what the EPA is saying, the EPA is now about 5-fold too low. And I want people to understand that. That's a big, big difference. Can you go back to that just a minute, Dizzy? Where do those EPA numbers come? They're not using the peer-reviewed literature at all. Their numbers are based totally on what industry reports to them. Industry tells them what the emissions are. There's no independent verification of that. Why did the numbers go down from 2015 to 2019? I don't think there's a chance in hell that that's because the industry really got better at this. It's because people were waking up to the fact that methane is important, and industry found it in their interest to report lower values. And since no one checks, no one verifies, they can report whatever they want, right? So those numbers are just completely bogus. And the methane emissions are substantially larger than people think. And that's true. That's a global problem. These are US numbers, but this would be true in, I think, any country, certainly Canada as well. Next slide. Okay, so let's go back to the global level. And this is the concentration of methane in the atmosphere. It's gone up rapidly in the 20th century. It actually leveled off. That's good news. It slowed global warming for the first decade of the 21st century. But it's been going up again since about 2006 or 7. And a lot of us have been trying hard to figure out what's going on there. It's actually accelerating. The methane increase in the last 2 years are the most rapid increase ever. So we're going in the wrong direction. Next slide. What's causing that? Well, there's an active debate. It's ongoing. I'm going to tell you my view. Their high quality, high visibility paper came out in Science back in 2016, and it says it's mostly biogenic. It's probably cows, right? Why is that? Well, as I mentioned, methane is this one carbon atom. It's got hydrogens around it. It's mostly carbon-12, that stable isotope. There's carbon-14 that's radioactive, but there's another non-radioactive isotope, a stable isotope, carbon-13, and we can monitor the change of that in the atmosphere and make some inferences, and that's been changing. So the authors of this paper inferred from that it was cows. Now, there are a bunch of problems with that because a lot of the spatial data, the satellite data, tell us that the increase in methane emissions over the last decade or so globally have been coming primarily from the United States. So if it's a cow source, that means emissions from cows have been going up in the United States. And that's just not the case because our cow populations have been going down and we're doing nothing else to produce more methane from cows. So there's a contradiction. And when this paper came out, it kept me awake for quite a while, weeks and weeks and weeks, years, trying to figure out why. And I took it on as a scientific challenge. And the next slide is just to show you that I published a paper on this, challenging the assumptions behind that paper and challenging the science. Next slide. And I'm not going to go into any depth here. I just want you to understand that the science is complex, recent, and rapidly changing. I started with the assumption that the most likely change is the shale gas revolution, which has occurred in the United States and Western Canada. Because prior to about 2005 or 6, it was impossible to develop shale gas. That's the methane that's trapped deep in the earth in shale formations. And only in this century has the technology been around to break it up. fracking, high volume hydraulic fracturing and high precision directional drilling. So since about 2006 or so, there's been an explosion in shale gas development, methane shale, in the United States and in British Columbia and Alberta. And most of the increase in natural gas production globally in the world since then has been in Western Canada and the United States. And if you want to imagine some change that's happened in the United States since methane started rising in the atmosphere in 2006 or so, you go, that's shale gas. That's what happened, right? The original paper said it can't be because of this carbon isotopic signal. It just didn't work. So next slide. And I believe they're wrong. And the reason here is that methane, CH4 there, is coming from this gas-rich shale, which we're now able to get out through fracking. Historically, some of that would break free anyway over hundreds of millions of timescales and would migrate through sandstones until it got captured in a reservoir of conventional natural gas. And the people who said cows are the issue assumed that the carbon chemistry of conventional natural gas and shale gas were the same. And next slide. And I argued that that's not true, because as that methane migrates out of those shale formations over hundreds of millions of years, some of it's consumed in that sandstone, it's oxidized. And that changes the chemistry of it in a way which makes it gives a signal to that conventional natural gas that is different than the shale gas. And when we started developing shale gas, it has a carbon signal that looks more like what cows do. And the authors of that cow paper missed that completely. So when we reinterpreted the study, next slide, little busy slide, but let me just show you the blue numbers are the numbers from that 2016 paper. And we're looking at the increase in methane globally from fossil fuels on the top and from biology, cows on the bottom. And they were saying there's about an increase of 4 teragrams per year from fossil fuels and an increase of about 21 from cows. When you reinterpret it to make this correction for the fact that shale gas is not chemically quite the same as conventional natural gas, you get the red stars, which were published in my paper. And we say fossil fuel change, mostly shale gas, mostly in the United States, is about 18 teragrams of there, and the cows are much smaller at about 10. So fundamentally different. The biggest change, the driver of increase in methane is shale gas. Next slide. And if we put that into a global perspective, updating the figure I showed you before, so the red numbers are now in 2015. Global methane's increased. It's increased about 25 teragrams per year. That's all from human sources. A lot of that is from oil and gas, mostly shale gas, again, mostly in North America, and a little bit from animal agriculture. So when we're looking at the problem, we really need to think about fossil fuels. And again, the IPCC is not caught up on this at all. They're 3 to 4 years out of date, and this is science is too recent for them. Next slide. Okay, so let's look at what we do about this. And I just, a little bit of history. Back around 2000, the oil and gas industry promoted this idea of natural gas as a bridge fuel, where we weren't quite ready to move to a renewable energy future, but we could move away from coal and move towards natural gas and be helpful, because when you use natural gas instead of coal, you reduce carbon dioxide emissions by about 40%. It's just a richer energy source. Next slide. And I started to worry about that logic back in 2009 or 10, and we published a paper on it in 2011. And what we said is, again, with the shale gas revolution, shale gas is methane, and if we're increasing the methane emissions from that, methane is such a powerful greenhouse gas that it could counteract the benefit from the carbon dioxide reductions from switching from natural gas to coal. So next slide. And this is from our original paper back in April 2011. And we're looking at the right, we're comparing the greenhouse gas footprint of shale gas, conventional gas, coal and oil. And the numbers for both shale gas and conventional natural gas in this paper are highly speculative because there is very little data. This is the very first paper anyone published on it. And we're pulling stuff out of non-peer-reviewed industry sources and things, trying to document it, but it was poor. The emissions show that the blue are the direct carbon dioxide emissions from using these fuels. The little dark red lines are small carbon dioxide emissions from the energy that's needed to process the fuels, develop the fuels. And the magenta colors are the methane emissions, unburned methane associated with using all of these fuels. And they come with all fuels, but it's worse for natural gas or shale gas because fundamentally those are methane. And these are converted to carbon dioxide equivalencies on a 20-year time frame. And what we said is, indeed, if methane emissions are as bad as we think they might be, this is no bridge fuel at all. It's terrible because of methane emissions. Let's take a close look before we continue to promote this. Next slide. And we got a huge amount of press attention. New York Times covered the day it came out. A lot of industry pushback as well. It's covered in thousands of newspapers. But we sort of shook up the world, and we shook up the science community too, so that hundreds of other people started making these measurements, and we now have a much better sense of what's going on. Next slide. Which is shown here. These are what I think the most recent data are. We now have over 1,800 peer-reviewed science papers on it. Again, ours back in 2011 was number 1. And so this is a huge change again in the science. And I've changed the color code on you here. Sorry about that. Carbon dioxide is now yellow and methane is red. But the natural gas has, whether shale gas or conventional, has a greenhouse gas footprint that's at least as bad as coal, perhaps bad, worse. And that arrow there has to do with whether we include the urban distribution emissions or not. It's a detail. But the bottom line is, this is not a good, natural gas is not good for climate, no bridge fuel. Next slide. And this idea of a bridge fuel, it died out. It's because of our work and the thousands of other papers, which basically supported that. So we're moving on. And I want to move now to a New York context. Along the way, New York banned fracking for shale gas back in 2014. And yet in the United States, our use of natural gas has risen faster than any other state in the country. And we don't develop much of our own gas anymore. We're importing it. And we're importing fracked gas from Pennsylvania, mostly West Virginia, Ohio. And it's got high methane emissions associated with it, but they're occurring outside of our state. But it's bad, right? So next slide. And I started to worry about that aspect of it back in 2013. So Bruce mentioned Mark Jacobson, who gave one of your presentations a while ago. Mark and I and others published this paper back in 2013. It's actually the first of his solutions papers. And we wrote a detailed plan of how to move the state of New York to a fossil fuel-free future. Next slide. Next slide. Yep, thanks, Des. And people paid attention. But the bottom line here is that this is from our paper. And we're looking from 2000 up to 2050. Keep in mind, we published this in early 2013, so time has passed since then. That top line is the projected demand, energy demand for all uses in New York State. And if we move down those two gray areas to the top of the fossil fuel line there, the difference is moving to beneficial electrification of transportation and heating, so heat pumps and electric vehicles, et cetera, and some increase in other efficiencies, better weatherization, et cetera. The higher net efficiency of those technologies means that we don't need anywhere near as much energy to produce the same end result. At the same time, we move away from fossil fuels and we bring in solar, wind with, of course, appropriate storage, et cetera. Next slide. And I'm really happy to tell you that I've done a lot of science which has made no difference in the policy world, but this paper made a difference in the policy world, and it eventually, over another 6 years, led to this thing called the CLCPA, the Climate Leadership and Community Protection Act of New York. And here you can see our former governor, Andrew Cuomo, signing it with former Vice President Al Gore looking on. This is the most progressive legislation for climate of any state in the United States. And the technology of it is based on our 2013 paper. Next slide. And it does these things, and I see I'm running short in time, so I'll go through it quickly. Let me just talk about the top two things here. Talks about a new way to account for greenhouse gas emissions, and I'm going to say a little bit more about that in a minute. It also says we reduce our greenhouse gas emissions from all energy use statewide by 40% by 7 years from now. Next slide. Doesn't say precisely how to do that, but it set up this commission, which is called the Climate Action Council, to do that. And I'm a member of it. We have statutory authority, so we're required by law to have a detailed plan as to how to meet these goals, which has to be published next month. I was in Albany yesterday working on it. We're meeting very, very regularly. We're on target to meet these goals. I want to be optimistic about that. These are about a third of the members showing you down there. Next slide. And just a little bit on the methane accounting. We do two things. And again, this is driven by the fact that although we banned fracking in New York, we're now using an incredible amount of fracked gas from Pennsylvania. So this law says we take responsibility for those methane emissions, even if they occur in Pennsylvania, if they're associated with our use of gas. So we no longer have a geographic boundary for our greenhouse gas accounting. It's a responsibility consumption based. And we also say the 100-year time period, which all other governments in the world use for methane, is crazy in terms of what the IPCC tells us we need to do now. Should be 20 years, and that gives a much higher ranking to methane. So next slide. And it's made a difference. This is from a Politico reporter, put out a tweet in the spring, and as she says, thinking about how you account for greenhouse gases sounds like a big yawn, right? I mean, I was a little offended when she said that because I'm the one who wrote this greenhouse gas accounting. I thought it was exciting. But anyway, it's a yawn. Yeah, except that it really changes fundamentally how you make it, things work. And as our commission has come to grips and politicians have figured that out, it has changed our focus. Next slide. And fundamentally, what it does is means these are our greenhouse gas emissions by percentage statewide for New York. Buildings, how we heat our homes and commercial buildings is number one. It's a big number one. That's because of the methane accounting. Under the old system, it was a distant 4, and no one was thinking about what we do for buildings. We're all thinking about transportation and electricity. So it's changed the focus. We need to reduce greenhouse gas emissions from buildings. And next slide, just to bring it back, looking at methane now. These are our methane numbers for New York under the new accounting, and methane's about 37% of our total greenhouse gas accounting. And the next slide, the biggest numbers there to look at are these 47 million metric tons of carbon dioxide equivalent per year of methane from our building sector. That's the biggest one. Next one down there is solid waste, though, and Bruce was talking about the need to do stuff with food waste and all, and what you guys can do is in urban in municipal settings. It's important. This solid waste methane is the garbage that we put in our landfills that becomes methane there. So keeping it out of there is critical, and that's something you could really do. Next slide. I just want to point out that we have a plan to reach the targets. We think we can reach the targets and do so economically. Next slide, since I'm a little short on time. Buildings are the biggest ones, and we're doing a couple of things. We're proposing to prohibit the use of gas and other fossil fuels in new home construction by a little over a year from now, and longer in other ways. But fundamentally, we also have 6 million single-family homes that are heated with fossil fuels in the state that we need to retrofit, and we have a plan for doing that. But the key is to move aggressively away from natural gas very quickly. Next slide. And we're in agreement on that. Bruce already talked about heat pumps. I'll leave it aside. This is my home. I've been heating my home for 8 years now with a heat pump. It works. I'll guarantee it's an old house. It actually works. Next slide. One more, please, since we're short on time. It's just, yeah, I want to end with this. This is really my last slide. How do we reduce methane emissions from natural gas? Stepping back generally. And I've been asked this question a lot, and this is from a briefing I gave at the White House back when President Obama was still president. And of course, people lost interest for 4 years under Trump, and we're just starting to catch back up. But I still believe what I said then, which is that the best way is to move away from natural gas as a fuel as quickly as possible. And in New York, our plan is to reduce within the next 8 years, cut our use of fossil gas by a third, cut it in half within the next 15 years, and get rid of it totally in 25 years. There are things like venting and flaring, and we can talk about that, and the regulations that Bruce was talking about. A lot of that has to do with trying to do a better job there. The problem is that the current plan is all based on industry self-reporting for verification, and the industry's not honest. We know that, and EPA needs to move beyond trusting them. But I want to talk specifically about this pipeline delivery systems that run through many communities, because they leak like a sieve. And I often hear people say, well, let's put money in and fix these leaks. You know, New York City, a lot of the pipes, half the pipes are more than 100 years old. They leak like a sieve. Should we rip up all the city streets and replace them? That would cost hundreds of billions of dollars. And personally, I think we should leave them there, simply move away from fossil gas as quickly as possible and abandon those systems, as opposed to putting the resources into fixing them. So I will leave you with that thought in my next slide. Just acknowledge that the Park Foundation and my university have been big supporters of what we've been doing for a long time, and I appreciate that. And we have this little site, howarthlab.org, where you can find much of the papers and other talks and things I've been giving you tonight. So
thank you so much, Robert.
Thank you.
Information, your presentation is so informative, and I'm so sorry that we needed to put you kind of like in a space that you needed to go very fast through the slides.
That's fine. I tried to pack too much in. That's my bad.
But it is so informative and very interesting. We are just on time, so I would just say for those who need to leave that we are going to share the slides and the recording. And Robert and Bruce, if you are okay to stay like 2 more minutes so we can answer at least 2 questions, because they were coming. We had some questions. Is that okay with you?
I'd be happy to stay. Yeah, and sorry for running over.
No, it's not your fault. It was just both information, both presentations were good. Thank you, Bruce, as well for your presentation. I'm going to move to the questions. First of all, there were a couple comments about that. Unfortunately, in Canada, in BC, the term bridge fuel, it's also used. But I'm going to move to the question.
We have to get rid of that. The bridge fuel idea is dead. Come on, move on.
Yeah, which is, I guess, can you elaborate on like how you can shift the narrative? How I'm guessing that the person that is asking is working in the area that they can communicate that. What would the narrative?
Yeah, I think emphasizing that. I mean, again, the whole bridge fuel idea was based. It has 2 premises. One is that we can't move immediately and quickly to renewable energy, and so we have to continue to rely on fossil fuels. And secondly, that if we're going to rely on fossil fuels, we should switch out coal and move to natural gas because the carbon dioxide emissions go down. The first premise is wrong. I mean, at this point, we can move very quickly to renewables. We do not need any bridge fuel. There's no need for that anymore. In fact, in terms of new construction in most countries of the world, including Canada, it's cheaper to produce new electricity from wind and solar than it is from a new natural gas power plant. So that first start of the premise is wrong. And the second part of the premise is also wrong, because although when we switch from coal to natural gas, the carbon dioxide emissions go down, the methane emissions go up. And the methane emissions are a huge driver of climate change, and they end up perhaps even accelerating. At the very best, we sort of hold our own and there's no net change. And at the worst, we accelerate the warming from that transition.
Right. Thank you for answering this. There are a couple more questions. Could you elaborate on why you propose banning flaring?
Oh, flaring. Flaring is when there's a methane release, you burn it, right? And it becomes carbon dioxide, as opposed to venting, which is putting the methane out in unburned form. And there are a couple of problems. There's a new study showing, just published last summer. People finally went out and measured what's going on when you have these flares, the burns, and even when the flames are constantly going and they really are burning things. The burn is not 100% effective. There's still a fair amount of a methane that's left unburned and going into the atmosphere. EPA and I'm sure the Canadian environmental authorities have always assumed that when you burn it, it's all burned, and that's just not true. The other problem is that the flares go out, the fire goes out, and they're just pumping pure methane into the atmosphere unburned. And methane's an invisible, odorless gas unless you're out there with fancy equipment, or now with satellites, which is a huge change. Couldn't do this 5 years ago. Unless you're out there, the average person wouldn't see anything wrong. And yet there's a huge, massive amount of methane. So we need to move away from that. And why are we doing that anyway? It's a lot of the flaring happens in say the Dakotas and part of the Alberta fields where industry isn't particularly interested in natural gas. They're really going after oil, and they just end up with the methane natural gas, and they find it a nuisance, and so they just get rid of it. And both Canadian and US government require them to burn it and flare it in order to cut down the methane, but no one's monitoring that. No one's enforcing it. It's not effective.
Right. I don't want to overuse your kindness to agree to join us, but maybe just one more question.
But fine by me. It's been a long day, but at this point, I'm fine with another 5 minutes.
Okay.
I was in Albany this morning, which is a 4-hour drive. Meeting with this council yesterday, and our plan has to be finished next month. And although I projected optimism, we're there, and I believe it. There are diverse political aspects represented on the council, and the oil and gas industry interests are pushing back very, very hard on us before we finalize this plan. So I had a very busy, tiring day yesterday and drive this morning.
And thank you for joining us for this. We are curious if this is the information that is going to come up from your committee. Is that going to be a publicly available information?
Yes. Yeah.
So
we were required by law to have a draft plan last December, and then we put it out for public review, and we got tens of thousands of pages of comments on it, and we did hearings, and we got well over 1,000 people show up and give comments in person, and we've been sieving through those and revising it. And the draft plan at the moment is not publicly available, but we will have a full new draft plan available in less than a month. And on December 19th, we will finalize it, and it will be out on December 21st, publicly available.
Great. We'll be following up with this information. Very quickly, if you can talk about how the reduction of fossil fuel use and increased renewable energy affects the planet due to mining and production of batteries and wind and solar generating machineries.
Yeah, that's a good question. The plan, the original Jacobson et al. Plan that we published back in 2013 made the case that we can do it all with wind, solar, and hydro. We don't need fossil fuels at all. We don't need nuclear, et cetera. You do need some storage, but perhaps not as much as you think. The detailed plan that the state is putting out now, we do have 5 existing nuclear power plants in the state, and we're calling for keeping those operating as long as they're safe and relicensed, but phasing them out as they become older and moving 100% away from that. We need some storage, and storage can come in the form of hydrogen that's generated when there's surplus electricity from wind or solar, but it can also come from compressing air and feeding the compressed air back through compressors, or liquefying air, or pumping water and feeding it back through compressors, or using flywheels, or there are about a dozen or so types of technologies, and we are agnostic as to what the best of those technologies will be. In terms of the actual capacity, we think the storage capacity has to be equivalent to about 18% of our renewable energy production capacity. So it doesn't have to be equal to it. It's a relatively small component. And that's partly because we can also manage demand, particularly when you're using heat pumps. You don't have to you can have some thermal storage in buildings to buffer the need to have electricity instantly on demand all of the time. And we also, by increasing the transmission of electricity efficiency in the state, wind, say, it's true the wind doesn't always blow, but if you look at real world data for New York, most of the time the wind somewhere in New York is blowing. We're a big state, not as big as some Canadian provinces, but pretty big. And if it's calm on the eastern end in Buffalo, New York, well, then it's windy on Long Island and vice versa. And so if we overcapacitize the wind power and have strong electric grid combining it, we don't actually need all that much storage.
All right. Thank you, Robert. Thank you so much for your time and your great presentation and answering the questions. Thank you so much, Bruce, for your presentation and for being always here with us in this webinar series. Thank you, Devanshi, for helping me, and thank you to everyone who participated and was with us this evening. With this, we will conclude our webinar. Thank you. See you November 22nd is our next webinar if you're interested to hear more about how the war affected climate policies. And Bruce, I don't know if you wanna, if you have final remarks.
For a great job as always. Thank you, Gabby and Professor Howarth. I can't express how happy I am to have had you here. We did have to cram a lot in, but I think
sorry about that.
well, I'm sorry I went a little long too, but I think it's always better to have more than not enough, and I think most of the people will probably be happy with what we gave them. I hope that's true, and we welcome your feedback on that. So thanks a lot. We'll see everybody soon, and I guess this is me signing off, and we'll see you all later.
Have a good
Thank
evening,
you.
everyone. Thank you very much.
Take care, everyone. Stay safe.